So I want to talk about dynamics of very simple first order circuits. But I want to look at a different structure than is typically thought about. Typically we will often try to start with the simple low-pass topologies. And these are going to be what we typically call more sort of high-pass circuits. And these become a little bit clearer when we actually ask the questions of what happens with frequency. But these are a little bit different circuits, and they give you a different kind of differential equation. Most people will look at an RC circuit and imagine that the R must be here, the C is there, and you must have thought I made a mistake. And no, I really didn't make a mistake, because I easily could swap them and I could ask what kind of behavior would I get. And so, because you think, well, wait, this should be a low pass, and you're like, no, this is a high, and you're like, but I put an R and L, that's a low pass, and you're like, no, it turns out you actually get a slightly different dynamic. So you might think low pass, but these are a different topology than you would have seen in the high pass in these kinds of structures. And the differential equation system you get for both of these two is identical. It's still going to be, you're going to have a first order linear differential equation. The linear differential equation you get in both cases will be the same, it turns out, within one parameter. In this particular case, you can basically write, Kirchhoff's voltage law and go, here's the voltage of the input structure and the voltage of the capacitor and the output voltage all have to relate, right? And so the input voltage has to go through this capacitor and the output voltage. Okay, no problem. I also know that I can say that if I write KCL at this node, that V out over R is then got to be equal to the current going through this capacitor. And again, remember, it's not current going through it, but it's the current coming off this plate and the current going onto this plate. Currents are not going through there. If they are, you put a resistor in there. So, but that gives me a capacitance times the difference of that voltage over dt. And I'm just going to leave it like that for a moment. Because if you actually notice, I've got an R and I've got a C here. If I multiply those two things together, I get a time constant, just like I would have had in a typical low-pass structure. All right. So in that situation now, what am I looking at? Well, my V out now looks like it equals to tau times dV in minus V out dt. Well, this is linear, so I can separate dV in and dV out. So basically take the dV out term, move it over to the other side, and I get this interesting differential equation, which looks very similar to a low pass, except that now I'm dealing with the derivative of the input voltage. Something is different here. So instead of just getting sort of just a sort of filtering operation, I'm sort of slowing things down, I'm actually looking at the things that are happening faster are the things that are actually showing up in the circuit. I can see the same thing with an inductor, but now I have an R and an L in the circuit. I would know that the current in the resistor has got to be V in minus V out over R. I also know that V out is equal to the derivative of the current through the inductor. So substituting the current in, I get this term L over R, which is then also its time constant. Again, same sort of thing we would have seen in the low pass case. But now I get this difference of V in minus V out. And in this case, again, this formulation gives me the same sort of prototypical differential equation. And it's kind of important to notice that I'm getting the same thing in both cases. And there is an incredible symmetry even between sort of low-pass structures, which have just a straight input term, and the high-pass structures where this is a derivative. Otherwise, these are our sort of canonical sort of circuit forms, and we kind of can build from these with, in terms of other circuits that we're going to kind of look at.